So since derivatives deal with rates of change, we can now look at some word problems, real life situations. If you can create a model for a situation, so here we've got bacteria and they're saying that this bacteria is growing at this rate. Well, if you can create a model for that bacteria, you can also take the derivative of that model and find out how fast something's growing at a specific time. So whenever we're asked for a rate of growth or a rate of change, that's telling you to look at your derivative and then find out how fast is it changing at that point. So if we take the derivative of this function, we're going to get 6t plus 15. Then at 10 hours, 6 times 10 plus 15, 75. What does that 75 mean? We can write a statement. At 10 hours, the rate of growth is 75. What are we dealing with? Bacteria. And our time is in hours. So it's growing at 75 bacteria per hour. So it gives you a sense of what's happening as far as the change goes at that time. For part B here, it says show that the number of organisms will always increase. Need to go back? Yeah, sorry. So our derivative was 6t plus 15. If you set that equal to 0, just to figure out what our graph is looking at, you're going to get t is negative 15 over 6, which doesn't really come into play because that's back in time. As far as your sign diagram goes, is if you made a sign diagram, if you were trying to show where this function is increasing and decreasing, plugging something less than negative 15 over 6, it's decreasing here, but anything after negative 15 over 6 is increasing. And the only number we're really concerned about is when time is equal to 0, because everything before that doesn't make sense. So your initial time at time equals 0, everything after time equals 0, the derivative is positive, and it's always increasing. So according to the model, the function will always increase. But if we think about a real life situation, is this plausible? Could this happen? I guess theoretically. But eventually you would think maybe the bacteria would run out of food, or maybe there wouldn't be enough space. So then something catastrophic would probably happen to the bacteria at that time. In fact, a lot of chaos theory looks at that. You have a model that works until you get to a certain point, and then it can't sustain it anymore, and then it goes through a period of chaos, and then it stabilizes again. So the main question I have right now with this question about mosquitoes is, with a cold April, does that mean we're going to have more or less mosquitoes in May and June? Less? Maybe. Maybe we needed it to get really warm, get all the mosquitoes out, then have this polar vortex come in and just crush them.
So mosquitoes always come out in moisture?
Yeah, they need some moisture. So was it warm enough to have them hatch and then they froze again, or I don't know. A lot of population questions have E in it. It's a natural occurrence that for that function, it works out nicely. So you'll see, if you do other questions, you'll see lots of population questions have the number e in it. T is measured in days. We're going to find the growth rate after 5 days. So again, the fact that we're trying to find a growth rate is telling us, find your derivative. The derivative of e is itself. Do you see that you have a chain rule here? And you'd have to multiply by 0.09. If we do that, we get that function. So then at 5 days, rounded, that comes to 35.3. So what does that mean? After 5 days, the growth rate (35 mosquitoes per day). That doesn't seem too bad. So all of these questions so far have shown if you can make an equation for that, then you can take the whatever the equation is looking at and look at a rate of change for that. So now here we've got a temperature equation based on time, so we can find out how fast the temperature is changing per minute as a result. So a couple things just to notice about this equation. You got a hot metal bar. We could figure out how hot this metal bar is right at time 0. If you put 0 in for time, e to the power 0 is going to be 1. You're going to add 90 degrees, so it's at 124 degrees Celsius. I think that's pretty hot. I'm thinking you don't want to grab this metal bar. You can see some things in this equation that what's going to happen in this metal bar is it's going to cool down. Can you see that it'll never get less than 34 degrees? Because this part, any function e to the x never gets less than 0. And so basically what's happening is it's cooling down and it's getting closer and closer and closer to the room temperature, which is 34 degrees, that it started at. So that's just some analyzing the question, trying to figure out what's going on with this equation. As far as solving it goes, we want to find the rate of change, so that's telling us we want to find our derivative. Our derivative here, another chain rule. And after 10 minutes, plug in 10 to there. Negative 2.436. So we can say the temperature is decreasing at a rate of 2.436 degrees Celsius per minute at 10 minutes. So I guess there would be a certain temperature at which if you touched a hot metal bar, it wouldn't burn you. You could calculate that temperature and find out the exact time that you could touch it without causing physical damage to your hand. And then you could find out if you did your math right at that moment by touching the hot metal bar. So you'd have to really trust your math. Hopefully, you know, it might just be that the question takes you long enough that by the time you're done the question, the metal bar is fine to touch anyways. But if you're quick at your calculations, then you'd have to know for sure, okay, I can touch it now. Probably you just wouldn't touch it. Get your friend to touch it, see, oh yeah, it's fine, try it. It's also smart strategy. All right.